Hey, welcome back, everybody. There for a moment, I thought I was going to do a solo lecture. Anyway, it generally happens like this toward the spring break, the last week before. A lot of people leave early. So if you haven't seen the schedule, next week is spring break. Okay. And when you come back from spring break, you'll have the next exam, which covers chapters 7, 8, and 9, of which 9 will be done with today. And then we'll jump into 10. So we're going to be a little bit ahead of the chapters. So any questions before I continue? Continue where we left off on slide number 5. Any questions? Okay, well, let us continue with this chapter. This chapter deals with an acid and a base. Let's refresh your memory. Okay, and there's 2 definitions of acids and bases. There's the Arrhenius definition, and then there's what's called the BronstedLowry definition. Okay, now with respect to an acid, both of the definitions are essentially the same. One produces a proton, the other one gives up a proton. Either way, there's a proton involved. Okay, to refresh your memory, what I mean by a proton, that is a hydrogen atom that has lost that electron and now has a plus charge on it. Okay, now that is the proton, and that is what causes the acidity property of these chemicals. And then the other definition was a base. Now, with respect to the Arrhenius definition, a base was anything that produces a hydroxide polyatomic ion. Now, we're talking about when we deal with acids and bases, we're dealing with aqueous solutions. So anything that produces is essentially telling you, when I put it in water, I'm going to produce a proton or I'm going to produce a hydroxide, okay? And so in both definitions, Arrhenius definition, proton and acid basically involves a proton. Where they differ is with respect to a base. The Arrhenius base is just simply very simple, straightforward, is anything that produces a hydroxide ion when it dissolves, okay? Which cut out a lot of potential bases out there. So BronstedLowry's definition is basically any chemical that will accept that proton. And there are chemicals, for example, we went over this, ammonia, that has nothing to do with the hydroxide, but it has, you'll find it to have lone pair. And even the hydroxide polyatomic ion, when you think about it, it's also encompassed as a Bronsted-Lowry base definition, because there are lone pairs of electrons around the oxygen as there is in ammonia, and the proton comes in and attaches itself to that lone pair. Okay, so when you get that reaction, and specifically a Arrhenius definition of an acid and a base, you produce what we call a neutralization reaction. Okay, neutralization reaction. Classic example, you have a little bit of acid problem, acid reflux, you ate something that didn't settle very well, get a little heartburn. What do you ingest? You ingest a base, Tums, Maalox, anything of that source, that type of material. That base then reacts with the acid in your stomach and neutralizes it and lowers the acid concentration in hopes that making you feel a little better, okay? Now, when you have an acid, in this case a proton, reacting with the base, and in this example a hydroxide, the product you always get is water. So a proton plus a hydroxide produces water. Water is neutral, okay? Then what else is produced is what we call the salt. The salt can be any salt. Here we use sodium chloride, but it's basically an ionic compound. So if we start with, think about this for a second. The acid here is a covalent compound. Notice hydrogen and chloride, okay? The base that it reacts with is an ionic compound. And so here's an example of a covalent compound and a ionic compound coming together. The proton gets neutralized to form water, and then what is left over are the respective salts, which would be, let me change the color here so we're on the same page. This is the cation of the base and the sodium ion, and this is the anion of the acid, okay? They come together to form the sodium chloride, otherwise known as the salt. Now, the salt doesn't, when you think with respect to chemistry, a salt is not just something you put on your French fries, okay? Because here, the general public thinks of a salt as being sodium chloride, and that wouldn't be incorrect. But you studying chemistry will know that a salt in chemical terms encompasses any ionic compound, okay? And in this case, we use sodium, but it could be any metal reacting, combining with a non-metal to form a salt or an ionic compound. All right, so this is your first example. The next chapter deals with chemical reactions. There are only 6 chemical reactions that really we're going to work with and deal with, and this is one of them, neutralization reaction. So you can eliminate one, you've been introduced to it, so you got 5 more to work with. In fact, you know of another one. If you drove your vehicle today, you put your vehicle use, unless you're electric, let's assume it's a combustion vehicle. You put gasoline in there and gasoline burn, that's a combustion reaction. So now you know 2 types of reactions. Okay. Now, the Bronsted-Lowry definition is, in both scenarios, we have an acid which produces and or loses a proton, okay? And the base this is where they differ. The Bronsted-Lowry's definition is any compound that will accept that proton. So it doesn't have to be the hydroxide, as the case with the arrhenius. And so here we have ammonia. As I stated earlier, ammonia, if you recall, we did the Lewis dot structure for that and had a lone pair on the central atom, lone pair of electrons. Compounds, atoms that have a lone pair on them had the property or the ability to accept protons. Protons have empty orbitals, okay? Remember, we talked about the hydrogen atom with a single electron, 1 proton, 1 electron, okay? When it loses that electron, it becomes a positive charge, just like any metal, but it's not a metal. It lost an electron, that has a positive charge. And now that orbit, which is 1s1 to begin with, now is 1s0. It's there, but it's empty, okay? That orbital that had 1 electron as a hydrogen atom is empty. There's supposed to be a 0 here, okay? And so now it has the capability to use that empty orbital to attach itself to any atom that has lone pair of electrons. And that's what happens with respect to, happens with water. Anything with lone pair happens with hydroxide. But here in ammonia, that lone pair attaches itself to form the ammonium salt, okay? And recall that is only one of the polyatomic ions that we list in the polyatomic ion table, okay? All right, so this demonstrates what a Bronsted-Lowry acid and base is. Now, with respect to the previous example, notice in the previous example, we had a covalent compound acid reacting with an ionic base. Here, we have a covalent compound reacting with a covalent base, okay? The main difference between the Bronsted-Lowry and the Arrhenius definition. Nevertheless, the bottom line is this: that proton has been neutralized by tying it up with the ammonia, forming the ammonium, in this case, chloride. Okay, so just like the hydroxide neutralized the proton with respect to Arrhenius definition, the ammonia neutralized the proton generator from hydrochloric acid in this example, and therefore rendering it, neutralizing the acid. Okay. All right. HCl loses the proton, and in this case, the ammonia gains the proton, and therefore is classified as a base. Now, with respect to strength, we have such a thing as strong acids and strong bases. Now, here's the key here that we're going to tell you this is a strong acid, this is defined as a strong acid, and this is defined as the weak acid. Now, how we define the strong acid or a weak base or a weak acid and a strong base, we define it by the quantity of ions that go into solution when you take either the acid and the base and you put it in an aqueous solution. If that material completely dissociates, roughly 100%, totally breaks up into the ions, then it's a strong acid. If that base totally 100% dissociates into all of the ions, it is a strong base. We will get examples where we place that acid into water, it doesn't dissociate 100%, maybe much less, maybe 5%. And that is a weak acid. And a good example of a weak acid would be acetic acid. Acetic acid is an acid, but it's very weak, okay, compared to hydrochloric acid, which is a strong. And the only difference between the two is the amount of material that dissolves in an aqueous solution. And that's simply put, that's what it is. There's a lot of ionic bases that, I just talked about the sodium hydroxide. There are a lot of ionic bases that are weak bases simply because when we put them in water, they don't dissolve in water very well. And we're going to utilize what we call here the solubility table. The solubility rules are why some chemicals, which will tell you which chemicals dissolve in water and which do not. It's going to be either soluble or insoluble. But keep in mind, even though it's classified as insoluble, it will dissolve a little bit, okay? And therefore making it a weak, in this case, base. And so strong and weak is a function of how much material goes into solution, okay? Some of the strong acids are given as follows. They basically ionize. In other words, they break apart into the ions totally roughly 100%. You say approximately because bear in mind, nothing's 100%. No, anybody fooled you. Nothing's ever 100%. So we have the first one, which you carry in your stomach, called hydrochloric acid, HCl. Now the others you don't. This one is called HNO3, nitric acid. And the other one here is called H2SO4, which is called sulfuric acid. We'll give you names here in a second. Now keep in mind, now you might ask yourself, boy, they look familiar here. Because if we break it up, we break HCl, guess what we have? We have the chloride, okay? Now the chloride has lone pairs of electrons all the way around. And that proton can come together. And when you have this, you have hydrochloric acid, okay? Now, does this look familiar from the polyatomic ions? Yeah, that is the nitrate ion, nitrate, okay? It came from HNO3, which is called nitric acid. Nitric acid was reacted with the base, okay? And the salt that was formed is the nitrate. And then look at the other one, SO4. Doesn't that look familiar with -2? That is called the sulfate. Remember the sulfate polyatomic ion table? Okay. Well, originally this came from H2SO4, and this is sulfuric sulfuric acid. Okay, and that sulfuric acid also reacted with a base, two hydroxides, to form the sulfate. So those polyatomic ions in that table, at least the anions, originally came from an acid, which then was reacted with a base to form their respective polyatomic anion ions. Okay. All right, so 3 examples of strong acids. They essentially, when you put them in water, they dissociate 100%. So hydrochloric acid breaks up. And remember, I had mentioned to you that hydrochloric acid is a covalent compound. Now, at the time, I said the main difference between, there's a lot of differences, but one difference between an ionic compound and a covalent compound is that ionic compounds, when you place in water, dissociate and break up. Some of them dissociate completely, some of them dissociate not so completely. And the covalent compounds do not. They stay intact when you put them in water, with the exception of covalent acids. And here's an example here, HCl, which is a covalent compound. And because the nature of the beast of it being an acid, it will break up into the ions of the proton and the chloride ion, okay? And this basically occurs 100%, and therefore we have a one-way arrow from left to right. Very little going back the other direction. Very, very little. It'd be like a tiny, tiny, tiny little arrow. Okay, so essentially all from left to right. Strong bases, here's 2 examples. Potassium hydroxide and sodium hydroxide. Now, the reason they are strong bases is because based on the solubility rules, we're going to learn these rules. Sodium and potassium, anything, sodium, potassium, whatever it's attached to, is always classified as soluble. Okay, and being soluble means that basically 100% of it goes into solution. And so therefore we have a lot of hydroxide in solution, and it makes it a very strong base. So here we have an ionic compound, sodium hydroxide. We place it in water. Based on the solubility rules, it will dissolve 100%. So it breaks it up into the ions. Remember, ionic compounds and the acids, think of them as 2 magnets that when I put them in water, they break apart now, and the magnets are separated, one with a positive charge and one with a negative charge. Okay, and that's what's happening here. Now, though I can't really say that HCl is like a magnet, I'm just saying because the nature of the beast, that bond is broken, and we form ions in solution. If you ever have to draw the process, you got to make sure you show the charge, okay? Because there are ions in solution. Okay, so strong bases, which are ionic compounds, specifically hydroxide ionic compounds, the strong bases show 100% show to be classified as soluble in water, and therefore they're very strong. Okay, because basically all the hydroxides in solution. Good example of sodium hydroxide would be some liquid plumber. Liquid plumber is a very strong base made up of sodium hydroxide. Very strong conductor of electricity. Okay, in fact, we're going to relate all this to conductivity. You know, if I have pure 100% water, okay, 100% water. And I'm going to denote that by beaker full water. Okay, 100% water, nothing in there, is pure 100% water. And I put electrical cables in here. Okay, there will be nothing, there will be no conductivity occurring. Okay, nothing would happen, no electricity will pass through that water. because there's no way for the charge to go from negative to positive, okay, or positive to negative, either way. There's no charge. The moment I put ions in here, both positive and negative ions, okay, now I have a means for that current to go from point A to point B, and it becomes a conductor. If I have a lot of ions, like these strong acids and bases, then I'm going to have a lot of current going through that electricity, through that water, okay? And it's very strong conductor. If I have a little bit of ions, not so much current will pass through, and therefore it would be a weak conductor, okay? More on that here in a little bit. Now, sometimes I need to demonstrate or to show you, or you need to show us, either way, to depict graphically what a strong acid in the base looks like, okay, in solution. So hydrochloric acid, and this could be water, a beaker of water, which has in it some hydrochloric acid. We know by definition that hydrochloric acid is a strong acid, which means that it will break up into ions 100%. So we'll show it as follows. Here's the positive ions and here's the negative ions. Okay, I don't need to draw a lot of them. I can draw 3 to 5 pairs to demonstrate that. I don't need to draw a whole bunch of ions, but I do need to make sure that I have, if I have three of these to begin with, then I'm going to end up with 3 protons and 3 chlorides, okay? You gotta make sure, in other words, it would be incorrect to show a diagram like this and only 2 protons. So you got 1 little chloride sitting there somehow magically not being stabilized by this counter ion, which would be the plus. So make sure they add up. So that one depicts on the left a strong acid, specifically hydrochloric acid. The one on the right demonstrates, shows, or depicts a strong base, because sodium hydroxide is classified as being soluble. Literally all of the sodium hydroxide that was together before we put it in the water, which, because it is a solid, we put it in the water and it completely dissociates. So again, if I'm going to show three of these, 3 sodium hydroxide, then I must have 3 ions of each one, the positive sodium ion and the negative hydroxide ion, okay? So notice that nothing's been drawn with the 2 together. You'll see that's how we draw a weak base and a weak acid. Okay, so strong acids and bases, the 3 of them, we have hydrochloric acid, we have nitric acid, and sulfuric acid, very strong acids. The strong bases, again, these are ionic bases. They have the sodium, and by definition, they're arrhenius bases, okay? And because of the solubility rules, they are soluble, classified as being soluble. These are soluble by classification. Now, what do I mean by that? Well, you know what? Let me take a quick second to demonstrate that, because we're going to be using it quite often. Here's the periodic table. Okay. On the bottom right side, we have what's called the solubility rules. Now, I want you to look at number 1 on the left-hand side, right here. Okay. Lithium ion, sodium ion, potassium ion, and the ammonium ion. And then look at the words always. What that tells you is this, that anytime a lithium whatever anion, or a sodium whatever anion, or a potassium whatever anion, or ammonia whatever anion, in this case it's a hydroxide anion, they are, those combination of those 4 are always 100% soluble, okay? 100%. So anytime you see lithium, sodium, potassium, ammonia, it's 100%. And when it's attached to hydroxide, 100% soluble, which then tells you strong base. Okay, strong base. When the partner for these four is the hydroxide ion. That's important. Strong base because they're classified as being soluble. Okay, and we're going to go through this table. You're going to see how we're going to utilize the table to determine whether something is soluble or insoluble. Because we got two sides. The left side is the soluble table, and then over here on the right side is the insoluble. Okay. Back. Again, what does strong mean? That means that they are completely soluble in solution and making them strong. And then they're going to produce whatever ions they have. Sodium hydroxide will produce sodium ions and hydroxide. Okay? Now, take a note here. If you notice a little trend here, when we talk about acids, previously I said to you, when we write the formula, like say this one here, 9 times out of 10, the first atom that you see is a central atom. So in this example, carbon dioxide, we've gone through these examples, okay? That's the central atom. And then anything that follows is bonded to that. The only one exception is by convention, people write water as follows, H2O. Well, in this case, the oxygen is a central atom. You know, you wouldn't, technically, it should be written OH2, but by convention, that's what the formula is, okay? Having said all that, you might ask, well, how do I know if I have an acid? Well, one little trend that you'll notice here all the acids. The hydrogen is written first, and like I stated earlier about 9 times out of 10, this is the central atom over here. 9 times out of 10, when you see hydrogen written first, that could be an indication that you're dealing with an acid. So I got to break it up because I know if that's an acid, I look to the right of that and see what follows. That means that I got chloride, if that breaks up, so that's legit, and that will work. And then I got NO3, which again reminiscent of the nitrate ion and polyatomic ion. Then we got sulfate. So that right there is like a flag to help you realize, do I have an acid? Well, occasionally, let's take an example of methane. You may see methane written as H4C. Okay, sometimes. Well, you might say, well, okay, well, I see hydrogen. Is it an acid? Well, I look immediately and I don't recognize carbon sitting by itself as far as being an anion, okay? Carbon by itself is not a very good anion. So this would tell me, no, I'm not dealing with acid, I'm dealing with methane, CH4, okay? It kind of helps you out to kind of help you determine, because you could be given the formula HNO3, and you have to recognize it as an acid, okay? All right, now we have strong acids, strong bases. We also have weak acids and weak bases. And by definition, in both cases, it just simply means that when I put them in water, they're not going to dissociate 100%. In fact, they're going to dissociate much, much less, maybe 1 to 5% dissociation, okay? So back to the number of ions in solution, they have very little, which means they're going to be weak as far as we use it to measure conductivity of electricity. They will conduct electricity, but very weakly, okay? There's a little conductivity test you can do if you want to look and see if you got ions in your water. You put the instrument in there and it has a little LED readout, and you can look at it, and if you have ions in solution, it's going to light up. It's going to light up depending on the ions, very bright, which tells you got a lot of ions, or kind of dim, which tells you there's very little ions in solution. So using that same instrument, if it's a strong acid and a strong base, that LED will read out bright. If it's a weak acid or weak base, the LED instrument would, you'll see it light up, but it's going to be a very weak LED lamp, okay? All right, so here we have this one. And anybody out there like Italian dressing? No, no Italian dressing fans here? I just want to say, if you are, this is what you're eating right here, okay? This is a formula for acetic acid, AKA vinegar. Okay? It's an organic acid. And the reason organic, we call it organic, we know because we got carbon and hydrogen involved with it. Notice the HCl we did earlier, it's not an organic acid, it's an acid, but not an organic acid, no carbon, hydrogen involved. And here we have a lot of organic acids, and acetic acid is one of them. Okay, we got hydrogen written first, okay, but we're going to tell you in this case, because, you know, if I need to do the analysis I just did, if I look right away to the neighbor, I see carbon. You know, carbon is not a good anion, but after carbon, there's a bunch of other stuff you're not familiar with. But if we ever use this as an example, I would definitely tell you this is the general formula for acetic acid. All right, so we got hydrogen there, and we put it in water. It will dissolve, but it doesn't dissolve 100%. There will be some protons in solution, and then its corresponding acetate. If you look at the polyatomic ions table, you will find in there acetate ion. The acetate ion came from acetic acid reacting with the base to form the acetate ion, okay? Now, because it's a weak acid, the previous strong examples had a one-way arrow. In this scenario, we have a two-way arrow, which is telling you that we have a lot of the starting material combined, not separated. If this were a strong acid like we did earlier with HCl, it would be a one-way arrow, just like I'm writing here. There's a two-way arrow, which indicates it does not break 100% apart. And so it would be a weak acid. Some other examples of those are H2SO4. Okay, remember, if you look at the polyatomic ion, guess what? CO3, that's called the carbonate polyatomic ion. If we put the hydrogens back on, we have this, which is called carbonic acid. If you drink a lot of soda pop like me, you drink a lot of carbonic acid. The next one is acetic acid, like that example we just did. And the third one is H2PO4, which is called phosphoric acid, also found in a lot of soda pop, but look at that. You know, polyatomic ion, we have the PO4 negative too. That's the phosphate ion. Well, the phosphate ion came from reacting phosphoric acid with a base and removing those hydrogens. Okay, so examples of weak acids. Now, how do we demonstrate? Oh, let me give you an example of a weak base, just like a strong base. Here's one we call MG. Oh, where's my pen here? MgOH. Okay, MgOH is magnesium hydroxide. I think they find a little bit of that in magnesium, milk of magnesia. There's some of it in there in that material. It's a cloudy material. If you look at a bottle of milk of magnesia and you let it sit there and got a clear container, it's cloudy. And if you let it sit there for a while, it's separated into the units. Now, magnesium hydroxide. Let's go back to the solubility table real quick. If you look at the where'd it go? Yeah, number 10, right here, the hydroxy ion. When the hydroxy ion is bonded to anything other than what's in number one, lithium, sodium, potassium, and ammonia. You know, earlier I said lithium, sodium, potassium are strong bases. Okay. If the hydroxide is bonded to anybody in number one, and if it's bonded to calcium, strontium, and barium, so there are 7 examples that the hydroxide ion is bonded to, which makes them by definition soluble, 100% soluble. Okay, that means that any other metal it's bonded to is insoluble. And like I stated earlier, even though it's classified as insoluble, there's always a little bit that goes into solution, but very little, maybe 1 to 5%. Okay, so in this example, magnesium hydroxide, by definition, is insoluble. Okay. There's only 7 soluble hydroxide examples, 7, the ones up here for number 1, and then those through strontium, barium, and calcium. Everybody else is insoluble. In fact, we can tap into that knowing we can react any other metal with hydroxide and cause it to be insoluble. and actually, excuse me, when you mean insoluble, the majority of it still is a solid material in the bottom of the container, and we can utilize that fact to extract other metals out, that unless, you know, other than the 7 we just talked about. And so that being stated there tells us that magnesium hydroxide is insoluble based on the solubility rules. Therefore, it has a double error. And yes, there are ions in solution, but the bulk of it, okay, is in solid form because it is insoluble. And the way we depict that in a diagram is as follows. Down in the bottom, this down here at the bottom of the beaker represents that chunk of material that settles down to the bottom of the container and is in the form of magnesium hydroxide combined. Now, when something is defined as insoluble, we have to show at least 1 set of ions, because yes, there are some ions in there. And so we have the 2 hydroxides, because there's 2 hydroxides in the parentheses and 1 magnesium ion with the +2. So that on the right demonstrates how to depict a weak base, okay? Or for that matter, any material that is classified as insoluble. On the left, we have HF, hydrofluoric acid, which was one of the, did I miss that? Yeah, I did miss that completely, HF right here. Hydrofluoric acid, just like similar to the name of hydrochloric acid, except this is with fluoride, okay? It is a weak acid, and we depict that as follows. Being a weak acid, we have to show at least 1 set of ions to show and to demonstrate that it is still a little bit of the ions in solution. But the bulk of the other material is still combined. Notice no charges on here. Now, it's a liquid, all right? And it will remain intact in solution. I'm going to demonstrate that, but I obviously tell you it's a liquid. Okay, so it would not be a solid like the case of magnesium hydroxide. This solubility, remember, only deals with ionic compounds, okay? HF, if they're insoluble, any covalent compounds that are insoluble or weak acids would just go in solution. Just like carbon dioxide in your soda pop. Carbon dioxide is insoluble, but it still is dissolved, if you will, or in the soda pop. If you don't believe me, take your soda pop. What happens when you shake it? You drive that carbon dioxide away. If it were that soluble, it wouldn't be driven away. It would still be in solution. Okay. All right. So this is how we show graphically on the left a weak acid, in this case hydrofluoric acid, but we could have used any of the other ones, carbonic acid, acetic acid, and phosphoric acid. And then on the right is how we depict any insoluble weak base, in this case, magnesium hydroxide. All right, so here are the weak acids: hydrofluoric acid, carbonic acid, phosphoric acid, and good old-fashioned vinegar. And then the weak base, in this case, is a magnesium hydroxide. But bear in mind, for the hydroxides, we use the example of magnesium hydroxide, but based on the solubility rules, unless they're bonded to those 7 examples, any other hydroxide is also a weak base. Copper hydroxide, okay, iron hydroxide, okay, they're all classified as being insoluble with respect to the solubility rules, and therefore would be a weak base. Okay, again, what does weak base mean? It's just basically showing you that they don't, what it means is not enough ions go into solution. Okay. Now, here's 4 diagrams, and they're asking which is a strong acid. Okay, so strong acid, which you guys think would depict a strong acid of these 4 diagrams, A, B, C, or D? What do you guys think? Any ideas? How about A? Yeah, look at those pictures. Okay, they're given to you in generic form. It's not it's not telling you A is not a compound here. Anything, it's just a very generic form. And so when you look at the pictures, and then you think back, well, okay, what's an acid? Well, an acid is, again, anything that produces a proton, okay? And so we can see we got protons here, here, and here. Okay, no protons in D. So definitely D wouldn't be involved. So now we go back to ABC where they do show protons. You notice you got proton there, you got proton there. But when we talk about strong, we're talking about literally any chemical that dissociates 100%. Well, we can't pick, because of that definition, we can't pick B and C because they're not shown here to dissociate. They're still combined. So B and C definitely will be weak acids, but A definitely will be strong acids because you don't see any combined examples of HA. Everybody is totally separated, okay, into their ions. So this definitely A will be a strong acid. And B and C certainly would be weak bases. Excuse me, weak acids, not bases. Because even though they show protons in there, there's not that many. And there's 2 protons for B and 1 for C. So both of them are very weak. And if I needed to even define it further, if I needed to compare B and C, well, B would be a little bit stronger than C with respect to acidity, okay? So B and C will be weak acids, and B will be a little bit stronger because it shows more protons than C. And then the next one, which is a strong base, well, there's none here because we're not we're not seeing any hydroxides. In general, when you're talking about bases, 95% of the time, we're dealing with the production of hydroxides. All right, so this brings us to the pH scale. Now, the pH scale is nothing more than a mathematical number. Okay, that's all it is. Now, the scale runs from 0 to 14, where on the far left of the scale, you have what is classified as something that is acidic. Right here. Okay, something that's acidic, which is in the arrow starting at 7. 7 is classified as neutral. And I'll explain, I'll define it a little bit further here in a bit. So 7 is neutral, okay? So anything less than 7 with respect to a pH value is classified as acidic. And anything greater than 7 is classified as basic. Now, within the range of acidic and basic, there's another degree of basicity, a degree of acidity, okay? So you could be, say, weakly acid, acidic, which can vary depending on the scale from, I don't know, from 3 to 6. And then you have what's called strongly acid. I've seen that scale run from 2 less. So in general, about 1.5 less is very strong acid. Same with respect to, on the other side of the spectrum, strongly basic could be as low as 12. You know, something like liquid plumber runs around 12-ish, okay, very strongly basic. And then milk of magnesia, like magnesium hydroxide, could be somewhere in the region of, say, 9-ish, okay? And then weakly acidic vinegar runs around 3. A lot of coffees and soda pops are around a little bit higher, okay? So that is a scale from 0 to 14. Now, how is that further defined? I got to introduce you to something, a concentration. We're going to learn a lot more about this later on. But when you see, for example, we got a proton written here, and then we put a bracket around it, okay? This is the concentration unit. Specifically, the units there's units of concentration called moles, M-O-L-E-S, per liter. We're going to learn a lot more about moles further down the road. In liter, you've already been introduced. So anyway, what it says here, that the concentration of the proton, when the concentration of the proton is greater than the concentration of hydroxide, then it's acidic, okay? When the concentration of the proton and the neutron are equal and the same, then it's neutral, the pH, okay? And whenever the concentration of hydroxide ion is greater than the proton concentration, then we have a basic solution. So if you think about this, you have an acid and a proton that come together to neutralize. So in the far left, the proton and the hydroxide mix together 1-to-1, and most of the proton is neutralized and the hydroxide neutralized. So what's left over is excess protons, which makes it acidic. On the far right, the same scenario. However, we have an excess amount of hydroxide, so it makes it alkaline. When you get a 1-to-1, if I have 10 units of protons and 10 units of hydroxides, they come together to react to form water, it's neutral, hence you have the central, okay? All right, so it's simply a mathematical value that comes from the concentration of the protons. And those units, as I mentioned, are moles per liter. with respect to the protons. Okay. And this is just a rehash of what I just explained. As far as concentration being greater, the proton concentration being greater in hydroxide, making it acidic. And vice versa, converse for something that is basic. All right. Now, what do I mean by mathematical equation? In your calculator, you have a button which we call the log. Okay. And if you are given the concentration, which at this point you'd be given what the concentration is of the proton, you would then just simply take that concentration, either in decimal format or in scientific format, depending on the value. And then you just simply hit the log button on your calculator and you get a number. In fact, you're going to get a negative number. So you take that number and you multiply by negative. This is why it defines the negative log of the proton concentration. Okay, so when you take the log of 10 to the negative 1 right here, if you take do it this way, take the log of 0.01, you end up with a -1 value. Okay, and then when you multiply it by a negative, you end up with a positive. So the pH will always end up with a positive number. Yes, you can get a negative, but for Chem 130, you're just going to see positive numbers. Okay. If you want to go back the other direction, let's say you know the pH and you want to know what the concentration is, there's a button called 10 to the X. You push that and you put a negative pH value. So you type in 10 to the X button and put a -1, and it brings you back to 0.1 as far as concentration. You can go both directions. A lot of times you have that. You're given the pH, you want to figure out what the concentration is, or vice versa. All right, so numbers that are a straightforward exponential here, units of 10. So 10 to the -5. If you take that, plug it in your calculator, you get log, you end up with a pH of 5. Okay. You'll see here that the exponent becomes what the pH is. Here you got 10 to the -8. Take the log of that. It becomes -8 times negative gives you +8. Okay. Notice that the concentration of the proton is extremely small here, 10 to the -8. You get a high pH number. Okay, because now you go into the alkaline range. Okay. You continue. You can 10 to the -3 will give you a pH of 3. Okay. Keep it in mind, pH of 7 is neutral, so that's acidic. You can either get the decimal number, 0.001, and you can convert that to scientific notation, which would be 10 to the -3, which is the same as what we just did here, 10 to the -3, the previous one. Okay. And then this one here again, which is 10 to the -8, which is a pH of 8. Again, very alkaline. Okay, alkaline. All right, so that's how we calculate it. Now, this is for nice and even numbers that you have, 1 times 10 to the, let's say 1 times 10 to the -7, things like that. But that's not always the case. Sometimes you got 2.4 times 10 to the -6, but that's not pH of -6. You'll see a totally different number here. So that's where you type in it, you put it into scientific notation, then hit the log button, and that'll give you the correct pH. Okay. Sometimes you need a calculator, sometimes you don't. It all depends on the value. Well, some examples of pH given here. Obviously, vomit, approximately 2, because again, you're coming up from a acidic environment. And that's why it burns in your throat and down your esophagus, because the tissues, you don't have the same tissues that your stomach is lined with to protect itself. So it burns. Lemon juice around 2.3. Coffee, it varies a little bit with the coffee. Saliva, again, that depends on your diet and what you're drinking. Blood, pretty standard. That's very important pH. It's slightly alkaline. Okay. Milk and magnesia, weekly basic, about 10.5. Ammonia, and about 11, a little bit stronger. Urine, it varies again on your diet and, maybe health issues and so forth. But and then most soda drinks are 2.5 to 3.5. And I was relatively surprised about root beer. It used to be one of my favorites, but it's a little bit higher pH, and that is acidic. Okay, that gives you an idea of the range of pH. If you have a swimming pool at home, I'm sure you got to check the pH. You got to maintain a good pH, otherwise it can affect algae and the formation of algae and so forth. If you have fish at home, again, you're maintaining the pH. So you're probably familiar with the pH. Now, this brings us to buffers. Now, buffers are nothing more than a mixture of chemicals that help maintain the pH of whatever you set it for, okay? And what it does, if you set for, say, pH 7, so you add enough of one chemical of an acid, you add enough of the base, you put them together. Then what happens if an acid comes in, it reacts with the base part of your buffer to maintain that pH. So your blood sugar, your blood, not the sugar, but your blood has a buffer in it, and it has to maintain a 7.4 value, well, roughly. Otherwise, there's all kinds of problems that can occur. So that's a very important buffer. So, all right. So you may have a reaction here, okay? You have HNO3, which hopefully by now you've realized that is nitric acid, okay? Then you have calcium hydroxide. Well, you might say, well, what do I have here? Well, here we have a parentheses of good old-fashioned hydroxides. Hydroxide is the base, okay? And then here we have the nitric acid. So we have an acid-base reaction, okay? Notice the hydroxide the calcium hydroxide has 2 OHs. So, if I have 2 hydroxides, when I put them in water, I need 2 protons, okay? And so that first one gives me water, H2O. And the second one would give me H2O. So guess what? I make 2 molecules of water because I have 2 hydroxide, which means I need 2 protons, hence the 2 there, okay? This is an introduction to balancing chemical reactions because reactions don't come together just simply 1-to-1. Some do, I should say. Let me restate that. Some reactions are real straightforward. So I got 1 of A, 1 of B, and I'm good to go. Sometimes it's different. Sometimes you need 2-to-1, 3-to-1. It can even be a 3-to-2 ratio, okay? And so what we have to do is we have to make sure we have enough of the atoms so that when at the end of the reaction, I still have the same number of atoms that I started off with. They may be in different forms, but the conservation of matter dictates that if I have 10 protons on the left, 10 hydrogens, I'm going to have 10 hydrogens on the right, okay? And so here, recognizing that I need 2 hydroxides, I have 2 hydroxides, I need 2 protons, and I can put a 2 in front of nitric acid. And knowing that tells me automatically it's an acid-base reaction. I make water, 2 of them, in fact, okay? And then I make the salts. Remember we talked about the salts? Here's the calcium and the nitrates. Calcium has a +2. I'm going to need 2 nitrates. And there's the formula. Now, let's do something here. All this brings us to this scenario, which is an introduction to balancing, keeping Mother Nature happy. If we look at the total number of hydrogens in reactants, I got 2 hydrogens here. And if you look at here for hydroxides, I got 2 hydrogens, so that's a total of 4 hydrogens, right? 2 of them in the form of hydroxide, 2 of them in the form of the proton. Look at the product side. I got 2 molecules of water. That means I got 4 hydrogens. Guess what? My hydrogens are happy. Mother Nature is happy with respect to my hydrogens. I got 2 nitrates, okay? Down here, I got 2 nitrates. So my nitrates are happy. NO3s, 2 NO3s. So Mother Nature's happy there. Got 1 calcium and 1 calcium. We're good to go. You have a balanced chemical reaction. Now, why do I need to know that? Because when we go and start, we're just introducing you here. A few more chapters down the road, we're going to be calculating, okay? And we're going to say things like, okay, if I have 10 grams of calcium hydroxide, how many grams of nitric acid do I need? Okay, and I'm going to use that ratio of 2 to 1. It's going to be very important. Or I may ask, if I have 10 grams of calcium hydroxide, how much water in grams am I going to make? And that ratio 1 to 2 is going to be very important in that calculation. All right, so let's go back to the subject at hand. So here to ask you, who is the Arrhenius acid? Who can tell me who's the Arrhenius acid? Now think about the definition of Arrhenius acid. Is anything that produces what?
Acid?
You got it. So which one of these 2 here? Okay, which one is the Arrhenius acid? Is it this guy or this guy?
It's the calcium hydroxide.
Ooh. Yeah, remember the term. Look at maybe this will help you. If this is the name calcium hydroxide, remember we've been talking about acids and bases, and that right there, hydroxide, isn't that a base?
Oh yeah, you did say the one in parentheses was the base.
Yeah, and so that makes this what?
The acid.
The acid, exactly. And so the nitric, by its name, nitric acid is the acid. It happens to be the Arrhenius acid, because what happens in net wise, let's look at what happens here. When we take nitric acid and we put in solution, I got 2 of them here, right? So I'm going to make the proton, 2 of them, plus I'm going to make the nitric ion, 2 of them. Okay, now the calcium, though it's a little more, when that breaks apart, I'm going to make 1 calcium ion and I'm going to make 2 hydroxides when I put them into solution, you see? And so these protons and these 2 hydroxides combine to form 2 waters. Right there, that's why we got a 2 there. And then what's left over is the calcium ion and the 2 nitrates that we need a parentheses here. So that continues over here, the calcium ion plus the 2 nitrates. So I put everything in ion so we can see what's happening here. See, I got 2 nitrates here, which is denoted by the 2 in parentheses, and then we got the 1 calcium. Then I got 2 waters here to separated. And so everything I put into ion so I can see the full picture. See, once I'm familiar with that, now I can understand hopefully why there's a 2 there in front of nitric acid and why there's a 2 in front of water. And if I count up all the hydrogens, I got 1, 2, 3, 4 on the left-hand side and 4 on the right-hand side in the form of water. My hydrogens are happy. I got 1 calcium on the left, 1 calcium on the right, and I got 2 nitrates on the left and 2 nitrates on the right. Okay. All right. So that's the breakdown of that particular reaction. And the calcium hydroxide is the Arrhenius base. Okay. And we know why calcium is bonded to 2 nitrates, because calcium has a +2 charge. Okay. And the nitrates each have a -1 charge right here. That's why there's a parenthesis around that, around the calcium nitrate. All right, so here we're going to draw pictures of nitric acid, hydrofluoric acid, calcium hydroxide, and magnesium hydroxide. Before we can draw pictures, we have to define them. Is there strong or weak? Now, based on what we talked about, this guy's a strong acid, okay? And this one is a weak acid. We demonstrated, we show you that's a weak acid. The potassium hydroxide, we got hydroxide, that's going to be a base. But the fact, because on the solubility rules, anything with potassium makes it soluble, which means that this will be a strong base. Okay, this would be a strong acid, weak acid. Okay. And then magnesium hydroxide, again, based on the solubility, it is insoluble on solubility rules, magnesium hydroxide, which means that this will be a weak base. Okay, so before I can draw any pictures of these, I first have to define whether they're strong or weak. So that means anything strong will be 100% separated. These 200% will be separated. The other two, as far the ions, 100%, everything's soluble. The weak, anything labeled weak, will show at least one set of ions, okay? One set of ions for the weak acid or base, just to show, and everything else would be combined, okay? All right, with that, we can go here, and there's a solubility rules I put in there. I'll demonstrate what that is. We just defined nitric acid as a strong acid. So we show that diagram wise with the ions totally separated and show at least 3 to 4 pair set. Okay. And don't forget to put the charges on them. Okay. So we got, at least here we showed 3 pairs, 3 molecules of nitric acid, and all of them went 100% dissolved. HF, by definition, was a weak acid. And so here show at least one set of ions in solution, okay? The rest of them, however many you want to put in, but at least minimum 3 to 5, put them together because they're not separated. So that depicts a weak acid. Potassium hydroxide, by definition, is soluble. Okay, look at the potassium there. Anything bonded to potassium, always soluble, regardless of what the partner is. That being the case, we recognize that is hydroxide. So the ions here are going to be potassium ions and hydroxide ions. And since it is soluble, based on the solubility rules, 100%, just like the nitric acid, totally dissociated. Nothing paired out. The hydroxides are by definition of soluble, they're defined as insoluble, okay? And so therefore, here's the hydroxide, unless they are bonded to these 4 here, or the calcium, the barium, and magnesium. Well, we're dealing with magnesium, so it is not soluble, it is insoluble. So we demonstrate with at least one set of ions, okay, which is the magnesium +2 and 2 hydroxides. And then down at the bottom is the material, the chunk of material that makes it insoluble. Okay. Where are we at? All right, to summarize this part as follows. Remember, arrhenius acids make or produce protons in water solution, okay? The bases, arrhenius bases, is any chemical that produces the hydroxide ions in solution. The other definition, the Bronsted-Lowry acids, they're like the arrhenius. They're going to produce, in this case, they're talking about losing the proton. All right, so they're similar in definition. Either way, a proton is being produced for both either arrhenius or Bronsted-Lowry definition. Where they differ is how they define a base. Where arrhenius base defines it as anything that any ionic compound that produces hydroxide ions. The Bronsted-Lowry has nothing to do with hydroxide ions. It just will accept that proton. Okay, hydroxide is not involved. And so the example I used was ammonia, or anything with lone pair that can accept that proton is defined as a Bronsted-Lowry base. Strong acids, we were talking about solubility, how they dissociate. If there's a strong acid, 100% roughly goes completely dissociates, breaks apart, or ionizes. Weak, much less, maybe 1 to 5%. Okay. The same is true for strong bases. They dissociate 100%. In general, the strong bases, pretty much most of the time, strong bases are ionic compounds that produce hydroxides. Okay. And based on the solubility rules, if they are soluble, based on the solubility rules, then they're a strong base. Okay. If they show not so much solubility, they're classified as insoluble, then they are classified as a weak base. Okay. And then buffers, all a buffer does is it tries to maintain a pH constant. And so you can create a buffer at any of the pH range values from 0 to 14. There's formulas to, to put the right chemicals together to give whatever buffer solution you want. Okay. All right, so erosion, pH is, here's some more pH and their ranges specifically, tap water, that really varies. I once had students when I was teaching in Kansas City bring in tap water from their area. Some live in rural areas, some lived in the city, suburbs, a whole bit. And I was really surprised the variety of pHs found in the water supply. In the Kansas City metro area, it varied from down to about 5, which is pretty acidic, all the way up to about 10 or 11, quite a range. So tap water, assuming, your source and so forth, 7.6. And then all the soda pops, my favorite down a long time ago used to be RC Cola. It's pretty acidic, 2.38. But even though it's acidic as they are, it's not as acidic as your stomach. Your stomach's a little bit lower. All right, so there you go. Why that could be a problem. Too much acid can affect your drinks. All right, well, I'm at 4:16. What I'm going to do is I introduce the solubility rules. What I want to do is really touch on them on Thursday. We're going to get a few more slides and we'll be done with it. We're going to stop it here. We'll stop on page 24. And we'll continue this chapter, which is not many more left slides.